Think about what you did today. Maybe you asked an AI to summarize a document, draft an email, debug a line of code, translate something, explain something, help you think through something you weren't sure how to think through alone. Now think about what you would have done if it was just gone. Maybe at some point in the last couple of years, for most of us, the answer to that question changed. It used to be, I would have figured it out differently. Now, it's something closer to, I genuinely don't know. We're not just using these tools. We are restructuring how we work around them, how we plan, how we create, how we make decisions. And that's not slowing down, it's speeding up. Which makes one question worth thinking about. What happens if it fails? Not theoretically, but in your day, concretely. What happens when a chip in a data center somewhere burns out in exactly the wrong place, and the service that you were relying on at that exact moment just stops? We've all been there. You open the app and it doesn't load. You've typed the message and nothing comes back. And the reaction is not mild inconvenience anymore. It's closer to being cut off. Because the real dependency is real, and it's deepening. And here is what makes that more than just an annoyance. The way these systems are currently built almost guarantees that it will keep happening. Not because the engineers are careless, because the architecture itself is structurally fragile in ways that are invisible from the outside. Google has been working on a solution to this, a fundamental redesign of how AI training works at the physical level. And to understand what they built, you first need to understand exactly how broken these current approaches actually are. The scale of computation required to train a frontier AI model is growing roughly 5 times every single year. The speed improvements from each new generation of hardware about 1.5 times per year. Those two curves are pulling apart fast, and the gap between them is where the fragility lives. Training a model at the frontier today requires on the order of 10 to the power of 26 floating point operations. Run that on the world's most powerful traditional supercomputer, not a modest machine, the absolute best one, and it would not take weeks. It would take 6 years of continuous, uninterrupted runtime. So, the current strategy has been brutal and simple. Take tens of thousands of chips, pack them into one enormous building, force them to operate as a single synchronized organism, compress 6 years into months by throwing everything at one location simultaneously. I introduce you to a data center, and that single location is where your problem starts. Every chip in that building has to stay in perfect lockstep with every other chip at every single moment of the training process. It is a three-legged race with 1 million participants. One person stumbles, and the entire line collapses. The whole cluster freezes. It diagnoses which component failed, retrieves a saved state from storage, and somewhat restarts. Not necessarily from the top, but it restarts. At the scale of 100,000 chips, a hardware failure is not a rare event. It is happening constantly. Memory errors, network hiccups, burnt out components. The cluster spends a meaningful part of its lifetime not learning but recovering. And every hour it spends recovering is an hour the service you are depending on is degraded or unavailable. There is a detail that makes physical reality of all this vivid in a way that is hard to forget. Inside a popular training framework, there is a flag called no blowup equals 1, which, well, what it does is instruct the processor to run fake computation, meaningless loops, dummy work with no purpose, not because the math requires it. Because if all those chips finished a batch and went idle at the exact same microsecond, the sudden synchronized power switching could physically damage the local electrical infrastructure. The building is running fake mathematics to protect the power lines outside of it. That is the system underneath the service you are using every single day. Now, Google DeepMind has been working on a fundamentally different approach, and the question driving it is, well, it's childishly simple. What if the chips did not have to wait for each other at all? The first step was an approach called DiLoCo, a distributed low communications training. Instead of synchronizing after every step, chips process their local data batches for hundreds of steps independently and only check in occasionally. Network traffic drops dramatically. But mathematical problem emerges. If chips are processing different data for hundreds of steps without synchronizing, their parameters begin to drift apart. And you cannot simply average them back together when they reconnect. Averaging divergent high-dimensional parameter vector produces something mathematically useless. A midpoint that destroys nuances, patterns each chip independently developed. The solution is to treat the divergence not as a noise to be averaged away, but as a signal to be interpreted. When chips check in, the system does not ask where they ended up. It asks what directions they were traveling. It calculates the trajectory of each chip's independent learning and uses that directional information to construct a unified update for the global model. 100 times less network bandwidth. Most of the quality of the training. But the original DiLoCo still had a vulnerability. It lengthened the time between the synchronizations, but the synchronization moment itself was still a single point of failure. Still, the same three-legged race, just with longer legs. The paper from Google DeepMind solves this completely. The architecture is called Decoupled DiLoCo, and the shift it makes is from synchronized batch processing to fully asynchronous systems. The analogy the researchers use themselves is a biological hive. A bee does not ask the hive for permission to forage. It does not wait for every other bee to return before it departs. It collects what it can, returns when it can, and the hive continuously integrates whatever arrives. The hive does not stop making honey because one bee got lost. In Decoupled DiLoCo, there are two roles. Independent learners, which pull a recent copy of the model, go off into their data, process it completely asynchronously, and return their updates whenever they happen to finish. And a central aggregator, the hive, which continuously ingests whatever arrives from whichever learners are active and constantly updates the global model in the background. The timing is completely decoupled. If a learner takes twice as long, if a network connection slows down, if a learner goes offline entirely, the hive doesn't care. It notes the absence and continues with the rest. The blast radius of any individual hardware failure is now strictly isolated to the one component that failed. To quantify this, the researchers ran what they call a chaos engineering test. a simulated cluster of 1.2 million chips, with continuous aggressive hardware failures deliberately inflicted across the whole system. Mean time between failures for any individual chip, 1 year. Across 1.2 million chips, that means the cluster experiences a component failure every single minute. Under those conditions, the standard synchronized training maintained useful compute time of just 18%. It spent 82% of its entire existence recovering. Decoupled DiLoCo, in the same hostile environment, maintained near 100% uptime, not because the failures stopped, because individual failures stopped mattering. A replacement chip boots up, pulls the latest model snapshot, and begins contributing immediately. No one waits. The computation never pauses. The service you depend on stays on. Now, here is where it stops being just an engineering story and starts being something that affects you directly. The old synchronized architecture required perfectly machined hardware. You cannot mix chip generations in a cluster where every processor must synchronize at every step. The entire system is bottlenecked by the slowest component, which means AI labs have been locked into purchasing tens of thousands of identical chips from a handful of dominant suppliers. The hardware monopoly is not incidental to how AI is built, it is baked into the structure. Decoupled DiLoCo breaks the dependency. The researchers successfully trained models using older and newer generation chips simultaneously. Fast chips and slow chips contributing to the same global model at the same time. The system weights each contribution based on how fresh and how large the data processed was. No compute cycles are wasted, and no single vendor holds a monopoly on the next frontier model. More vendors can compete, more options enter the market. Supply improves, prices fall, and that matters to you because the cost of the tools you are using every day is directly connected to the cost of the hardware building them. And then there's the energy story, which is it will show up in your life in the most tangible way. Right now, the electricity infrastructure in your city, in your neighborhood, is quietly being reshaped by AI. Mega data centers pulling enormous concentrated loads from the single point on the grid requires updates to local infrastructure. New substations, new power lines, new capacity. That cost does not disappear. It gets distributed across everyone connected to that grid, including you. Decoupled DiLoCo changes this in a fundamental way. Because the architecture reduces required network bandwidth so dramatically, the researchers trained a 12 billion parameter model distributed across 4 geographically separate regions in the US, connected by nothing more than standard commercial internet. 2 to 5 gigabits per second. No proprietary high-speed fiber. No bespoke interconnector. The kind of connection available to a large office building. If you do not need a single massive cluster in one location, you do not need to drain a single city's electrical grid to power it. You distribute the computational load. You spread the energy draw across existing infrastructure that is not being fully utilized. Each site pulls less. The grid at any single point is not overwhelmed. That means the substation 2 streets from your house does not need to be rebuilt to handle AI. The lines running through your neighborhood do not need to be upgraded on AI's schedule. Your electricity bill does not carry the hidden cost of infrastructure expansion driven by a single connected facility. The load is distributed, and distributed load is manageable load. Think about what that means for any country seriously investing in AI capability. You do not need to find one enormous plot of land, build one enormous facility, and negotiate access to one enormous power connection. You can build small, build distributed, connect each facility to existing load infrastructure at times or in places where that infrastructure has spare capacity. No single site is the bottleneck. No single community bears the full weight. Every country that builds this way does not just reduce its energy burden, it reduces its exposure to any single point of failure, hardware, power, or political. And then there is what the researchers call scavenging. Globally, enormous volumes of compute capacity sit idle. Facilities that have already paid for their hardware and their connections but are not using them fully. In the old synchronized architecture, you cannot recruit that idle capacity. The cost of halting the training run and resharding the model is just too high. A Hive architecture does not require halting or resharding. A data center that goes quiet for the evening can simply boot up the learner software, pull the latest model snapshot, and begin contributing over standard internet. 12 hours later, when it needs its capacity back, it disconnects. The Hive registers the drop and continues without pausing a single compute cycle. The system actively seeks out available capacity. It uses energy where it exists and is not already under strain. It is not asking the grid to build new capacity for it. It is using what is already there. That is a fundamentally different relationship between AI and the infrastructure that powers your daily life. So, what does it actually mean for you? It means the tools you opened this morning get to simply be there tomorrow and the day after, quietly, without outages, without the low-level anxiety of depending on something that might disappear mid-sentence. The infrastructure underneath it starts to behave more like running water or electricity, something you stop noticing because it no longer fails you. And yes, that stability will deepen the dependency. Honestly, the more reliably these tools work, the more we will reach out for them. The more complexity we will hand off to them. That trajectory can feel maybe unsettling if you think of it as offloading your thinking to something else, but consider what actually happens when the tool works the way it is supposed to. You hand it something dense, a paper, a concept, a system with 30 moving parts you do not have time to fully untangle. And it digests it, compresses it, hands it back in a form your brain can actually engage with. And then the real work begins. You reflect on it. You test whether you understood it correctly. You connect it to something you already know. You push on the edges of it. The tool did not think for you. It cleared enough space for you to think better. That is the future this architecture is quietly building towards. Not a version of humanity that thinks less, a version that gets to think about more. More people in more places with access to something that makes complexity approachable and difficult problems tactable. A world where the question is not whether you can afford access to these tools or whether the infrastructure in your country can support them, or whether a single hardware failure somewhere will take them offline at the wrong moment. The word for what that makes possible is not smarter. It is not faster. It's useful. Genuinely, practically, daily useful in ways that compound quietly over time and show up in what you are able to build, understand, and contribute to the people around you. That is what a research paper published this year by a team at Google is really pointing towards. Not a technical footnote, a step toward AI infrastructure that is stable enough, distributed enough, and resilient enough to be trusted with the role it is already playing in our lives. The Hive keeps learning, and so do you. And as always, thanks for watching.